Welcome to Derivatives Lesson 5, Higher Order Derivatives and Position, Velocity, and Acceleration. Okay, this section you'll have to take some paper notes. Sorry, I don't have anything written down, so you're just going to have to make do with this part. However, on some of the other notes with position, velocity, and acceleration, instead of taking notes, you can probably highlight some of the important things, because I think I have most of it written down for you. So let's go ahead and move along. Finding higher order derivatives can be extremely easy or painfully difficult. The second derivative of a function is just the derivative of its first derivative. The third derivative is the derivative of the second derivative. Alright, let's go ahead and show you how this works with a higher order derivative. Alright, you ready? I'm just making this right up on the spot. F of x equals 3x cubed plus 6x squared minus 12x plus 93. Okay. What is the first derivative? F prime of x. Oh, come on, you should be able to do this by now, especially when I give you an easy polynomial like this. 9x squared plus 12x minus 12. Let's go ahead and find the second derivative, which is the derivative of the first derivative, or the second derivative of the original function. We're going to call this f double prime of x. 18x plus 12. F triple prime, the derivative of f double prime, or the third derivative of the original function, is flat out just 18. And f quadruple prime is just 0. And if I try to find any more derivatives after that, it's just going to be 0. And that's how you take a derivative of a derivative function and take the derivative of that function and then take the derivative. Yeah, you get the point. Let's go ahead and move on. As you saw in the last example just drawn, all polynomial functions eventually go to 0. I wonder how many derivatives it would take to get to 0. Several, I'm sure. 5 or 6? How many did it take with x cubed? 1, 2, 3, 4. So I'm guessing with 3x to the 5, it's going to take 6 derivatives to get to 0. Okay? Rational functions, they get a boatload harder. Let's see if I can pick a simple one and show you. F of x equals x plus 1 over x minus 1. Okay, f prime of x. Hey, we get a good chance to use what we learned with the quotient rule and everything. So 1 times x minus 1 minus x plus 1 times 1 all over x minus 1 quantity squared. So f prime of x equals x minus 1 minus x minus 1 all over x minus 1 quantity squared. Alright, it's taken us just about 5 pieces of paper to figure out that f prime of x equals negative 2 over x minus 1 quantity squared. And I've already redone this once because I started to show you how to find f double prime of x, and I completely forgot about the chain rule. in order for us to do the second derivative, we need to know about the chain rule, and we won't learn about that till next week. That's why rational functions get a boatload harder. And Noah, I did redo this because the first time I did it, I had this section all over in this corner where you can't see because I'm the one talking in the corner there, so I redid it just for you. Noah, thank you for your concern to keep on reminding me about that. Some functions have higher order derivatives that are cyclical. I'll give you one. F of x equals sine x. Okay, the first derivative of sine x is cosine x. The second derivative of cosine x is negative sine x. The third derivative of sine x is negative cosine x. And the fourth derivative of x is sine x. Hey, we're right back where we started it. Alright, this is the way Leibniz would write it. The derivative of y with respect to x. That's the first derivative. The derivative of y, the second derivative of y with respect to, like that. Yeah, I know, it's so crazy. That's because this is the part that's being to the second power, d dx of y. The third derivative would be d cubed y over dy, whole thing cubed. Okay, and then the fourth derivative, d to the fourth y over dy all to the fourth power. Just the way of showing it with Leibnizian. Boy, I tell you what, Newton was a whole lot cleaner for the most part, although I like Leibniz at times. Let's move on before I talk anymore. The first derivative tells us about the rate of change in the original function. What does the second derivative tell us? The second derivative tells us how much is the rate of change changing. Go ahead and say, what? Think of it this way. Okay? I'm driving down the road at 45 mph. I have my cruise set so that I don't speed. That's usually why I use the cruise, is because I end up speeding if I don't. Now, if I tap on the brake, okay, I'm going to start decelerating. And that deceleration, my slowing down, will tell you also how much this velocity is changing as you slow down. So that's how you can use this, like a second derivative and rate of change. Alright, let's go ahead and move on. Rates of change, this is where, you know, we brainstorm in class. We don't have class now, so, you know, I'm thinking like 30, no, that's not a good rate. 72 WPM, 72 BPM. Let's see here. .45 RPM. Yeah, those were really cool records, by the way. 45 RPMs. Those were cool. They were called 45s. And, you know, rates of change. Something per usually a unit in time. Although not always units of time. Because, hey, you guys, you know, when you're standing up taking care of business, you know, you see this thing on there, you know, 1.6 LPF. I know some of you know what I'm talking about. Alright. Anyway, those are rates of change. Let's move on. All right, now we're getting into the position, velocity, and acceleration. And usually position, velocity, and acceleration are functions of time. That's why we have up here s of t. Position function is usually an s. Sometimes it's an x of t. S prime of t is the velocity function. Sometimes it's written as s prime of t. Sometimes it's just written v of t for velocity function. S double prime t is the acceleration function. It's also known as v prime of t or a of t for the acceleration function. Let's go ahead and move on. Okay. The average velocity. That's the change in position over the change in time. So how would you find out what your average velocity is? Well, let's say I drove 200 miles and it took me 4 hours. Okay? So my starting point was 0. My ending point was 200. So it is the position function at the end minus the original position function over the change in time. Now, instantaneous velocity, that is the limit as delta t approaches 0 of the average velocity. Well, doesn't this look really similar to what we've already done? Sure. Alright, let's move on. The acceleration function tells us how much the velocity function is changing. Acceleration is the change of the velocity per unit of time. I will let you go ahead and read these and write them down if you so choose, and then we will move on. Okay, I need to speed it up a little bit here, so let's move on. Vertical motion. Use position function as negative 1/2 g t squared, that's time squared, plus the original velocity times t plus the original height. And let's use that vertical motion with the problem that you have at the bottom of your paper. Suppose a person 160 feet above the ground tosses a ball. Okay, using the gravitational force and everything, we should be able to come up with the following position function. Negative 16 t squared plus, okay, what was the original velocity of the ball? It tells you 24, so it's plus 24t plus the original height. You're starting at 160 feet above the ground. Take the derivative of that, negative 32t plus 24. And then what is the height after 2 seconds? Sorry, what is the speed or the velocity after 2 seconds? Negative 32 times 2 plus 24. The velocity at 2 seconds, negative 40 feet per second. And then the first one asks you what time was the speed, the velocity, sorry, equal to 0. Set the derivative right here equal to 0 and solve. When you solve that for t, you get 3/4 of a second is when the velocity was 0. What was the highest height it attained? Well, that's when the velocity is at 0. So put 3/4 of a second in back to the original function. So its highest height was 169 feet when you replace 3/4 in. And then h double prime, go ahead and take the derivative of the first derivative. The acceleration function is negative 32 feet per second squared. To find the time when it hits the ball, set the original function equal to 0 and solve that quadratic. This concludes lesson 5.